This video contains a pink hippo puppet, examples about hearing loss, dating, and teddy bear therapy. I am physically assaulted by the hippo. Again.
So before we begin today, I thought we should all have a bit of spaniel love. Hello, spaniel. Because today's lecture is on null hypothesis significance testing. Not the funnest topic in the world, but if you've got a spaniel, it's all fine. In today's lecture, we're going to have a look at null hypothesis significance testing, or for most people, the p-value. So as we've seen in the previous couple of lectures, there are 5 key concepts to understanding the statistical methods that are typically applied in the social sciences. The standard error, which we looked at in a previous lecture, parameters, which we also looked at in a previous lecture, confidence intervals or interval estimates of the parameter, which we looked at in a previous lecture, estimation, which we looked at in a previous lecture, and that leaves us with one final topic, which is null hypothesis significance testing. So that's what we're going to cover today. So where does this fit into our model? Well, we've talked about this spine of statistics, that we always start off with some kind of scientific question that we're interested in answering. We will sample some data, visualize the data before we do anything. Then we fit a statistical model, and those models are invariably variations on the general linear model. And we saw that when we fit a model, there's 2 things we can think about. One is estimating the effect, so estimation, and we can do that with a single value, a parameter estimate, or an interval value, so we can construct an interval around the parameter estimate. And a second thing that we can do is to apply some kind of significance test to that parameter. And finally, we need to test the assumptions of our model and possibly fit a variant of the model that is robust if any of those assumptions are violated. So today we are focusing on this part of the diagram. So we've fitted a model, we have estimated our parameters and constructed confidence intervals, but we now want to apply some kind of significance test to them. So that's what we're talking about today. And I don't really talk about this too much, but draw your attention to the fact that the standard error, which we talked about in a previous lecture, is quite intrinsic to this process. So that feeds into both confidence intervals and hypothesis tests. Okay, so by the end of this lecture, hopefully we'll have some kind of understanding of the process of significance testing parameters, so what it means and what process we need to go through. I'm going to spend a bit of time trying to explain what a p-value represents and also what it does not represent, because it's another thing in statistics that there are a lot of misconceptions about. So we'll try to dispel some of those. We'll have a look at some of the limitations of significance testing. And we're also going to talk briefly about effect sizes, so looking at the parameters themselves and how looking and interpreting the parameters provides a useful context for significance tests. So what is null hypothesis significance testing? Well, this flow diagram basically illustrates the process that happens if you're applying frequentist models. Now there are other types of models that you can apply, Bayesian models for example, and they have a different process, but for most of what you'll read in psychology journals and social science journals, this is the process that people are supposed to go through. So you start off with some kind of hypothesis that you want to test, and having generated that hypothesis, you kind of split it into 2 alternative realities. A null hypothesis, which is effectively saying there is no effect, and an alternative hypothesis, which is the thing you're hypothesizing. So, for example, we might hypothesize that online learning leads to reductions in happiness. That's not a good prediction. Not a good prediction for me. But let's say you predict that. Your alternative hypothesis is that effect exists, so engaging in online learning reduces your happiness. The null hypothesis will be there's no effect of online learning on your happiness, so it doesn't do anything. So what you do, having generated this hypothesis, is you specify a significance level, and this is going to be basically the threshold that you apply at the end of this process. Now what you're supposed to do is to have a look at the research literature and know the kind of area that you're working in and generate a bespoke alpha level that is appropriate to the research that you're doing. You are not supposed to blindly apply a single value to all circumstances. So Fisher, who was responsible for the p-value part of this process, but not the hypothesis testing part, he said, I'm paraphrasing slightly because I didn't, I've not actually memorized his writing or anything, but he said something like, only a fool would use the same threshold for alpha all the time. So, what do psychologists actually do? They typically apply 0.05 and don't think about it. So rather than thinking about the bespoke alpha that they should apply, typically they just go, what does everyone else do? Oh, they use a 0.05 level of significance. Okay, I'll do that too. That's what you should not do, but that's what lots of people do anyway. So having decided on your bespoke alpha, what you should then do is use that alpha to calculate the sample size necessary to detect the effect of interest. And you would also pick an appropriate sampling distribution for the parameters that you're interested in estimating. So typically that distribution is a normal sampling distribution. I mean, at least most of the models that we're dealing, or most of the variations of the general linear model that we deal with, that sampling distribution will be a normal distribution. But that's just in the process to point out that you should actually be thinking about these things. So having done that, you've calculated the sample that you need to detect the effect, and let's say that's 98 participants. You then randomly sample 98 participants, no more, no fewer, and you estimate the parameters. So you fit the model, you go through the estimation procedure, you get some estimates of your betas, and based on those betas you can compute something known as a test statistic, which we'll talk about in a minute, and that test statistic will be putting those betas to some kind of test. Again, we'll talk about it in a minute. Having done that, so you've got this test statistic, well, I say you, I mean obviously you get a computer to do it because that's what computers are there for. You compute a long run probability P that the observed statistic would be at least as big as the one that you have observed if the null hypothesis were true. We're going to come back to this in quite a lot of detail, but essentially you calculate a p-value, and then you compare your p-value to the alpha level that you set at the beginning. And if your p is less than or equal to the alpha that you set at the beginning, then typically people use that as evidence that they can reject the null hypothesis. So in other words, if the test statistic that they obtained was very, very unlikely, so the p was very, very small, very unlikely, if the null hypothesis were true, then people say, okay, well, this was unlikely if the null was true, so we'll reject the null. However, if p is greater than the alpha that you set at the beginning, so if the p is kind of reasonably likely, if the null hypothesis were true, then you use that as evidence to accept the null hypothesis. So you say, okay, the test statistic I've observed is reasonably common when there's no effect, so I'm going to assume that there's no effect here. So that's the process in a nutshell. A very long, convoluted nutshell that probably contains a really rancid, rotten, disgusting tasting nut in the middle. So let's just recap the example that we've been using throughout all the lectures, which is to do with ears ringing, predicting the length of time the ears ring for as a function of the volume of concerts that you have attended. So this model should be familiar with you. We've seen it a number of times. I just want to illustrate how the beta, the parameter attached to a predictor variable, can tell us something about a hypothesis. So if we're hypothesizing that there is an effect of the volume of the concert on how long your ears ring for, then essentially we're hypothesizing that the beta attached to volume, which bear in mind represents the slope of that red line, it also, you can think of it as the rate of change of the outcome as volume increases. If that beta is not equal to 0, then there is some kind of relationship between volume of concert and ears ringing. So, and the degree to which it differs from 0 tells us the degree to which the volume of the concert affects ears ringing. So the beta very directly kind of quantifies the effect of interest. Now, under the null hypothesis that there is no effect, the beta would be 0. The line would be flat. So as the volume of concert increases, nothing happens to ear ringing at all. That will be represented by a flat line. So the beta attached to volume can be used to test a hypothesis, because if that beta is 0, there is no, if the effect is basically 0, and if it's different from 0, then the effect is non-zero. So we can use the beta, we can test whether the beta is different from 0, and that test will tell us whether the effect is different from 0, because the beta very directly quantifies the effect of interest. We looked at a variation on this example, which is looking at just whether you attend concerts or not, and how long your ears ring for. And this would be the equivalent to sort of comparing two groups, so groups of people who attended a concert and groups of people who didn't. And again, other things, we've seen before that the beta 1 in this scenario represents the difference between those two means, so the difference between the means of the two groups. So beta 1 again, so the beta for attendance very directly quantifies the effect of interest here, so whether there's a difference in ear ringing in the two groups. If that beta is different from 0, not equal to 0, then the difference between the means is not equal to 0. There's a slope to the line, so ear ringing changes as a function of group. Under the null, again, that line, the gradient of that line, the beta would be exactly 0. We'd see a flat line, which basically means the means in the two groups are the same. So all I'm trying to illustrate here is that we can use the beta attached to a predictor. Because it quantifies the effect of interest, we can apply a significance test to that beta. So parameters represent effects. So this could be the relationship between a predictor and an outcome, and the relationship might also be a difference between means of groups. And both of those can be quantified with a beta or a b. So parameters reflect hypotheses, which means that we can express the null and alternative hypotheses in terms of these parameters. So the null hypothesis, which we normally express as h0, what we're effectively saying here is the b in the model, the parameter, is equal to 0, or there may be situations where we want to compare two parameters, so you compare the parameters of two variables or something. So the null could also be that parameter 1 is equal to parameter 2, or two of the betas in the model are the same. The alternative hypothesis, that there is some kind of effect, that's normally denoted with h1. We can express that in terms of the beta not being equal to 0, so being bigger than or smaller than 0, or two betas in the model not being equal to each other if for some reason we want to compare the betas attached to different predictors. Now we know from previous lectures that all parameters, all b's, have an associated sampling distribution, which means that every single parameter that we estimate has a standard error attached to it. And the standard error is going to tell us something about how variable those estimates, parameter estimates, will be across different samples. So if you, hopefully you remember, small standard errors mean that different samples will give us pretty similar estimates of a parameter, whereas a large standard error means that different samples could give us quite different estimates of a parameter. So the standard error is really the kind of the noise, represents the noise in the sampling process. And the beta represents, so the estimate in your sample represents the signal. So we can construct a kind of a signal to noise ratio if we look at the size of the parameter, so the value of the parameter, that's our signal, relative to the noise there is in sampling, so how much variability there is in parameters across samples. So if we divide the estimate by its standard error, we're getting a signal to noise ratio of the parameter relative to the kind of uncertainty in its value. When we do that, we get a test statistic, so typically a t statistic in fact. So if we divide the parameter by its standard error, that gives us a test statistic, a signal to noise ratio. And once we've calculated that test statistic, we can, based on the properties of that test statistic, work out the likely values of that test statistic if the null hypothesis were true. So if a beta was 0, what values would we be likely to get of a particular test statistic? And we typically express this or we can express this as a distribution of probability. So the chart on the slide, the plot on the slide here shows one such distribution. So what we're kind of saying here is we're looking at values of the test statistic on the x-axis, and on the y-axis is the probability of them occurring. So you can see at very small values of the test statistic, the probability of them occurring under the null is very, very low, and very high values of the test statistic, again, probabilities are very low. Whereas if we look at the null, so the test statistic being 0, that's when we get the highest probability. So what we can see is we can look at values of the test statistic and work out how likely they are to have happened if the null were true. And what we do then is we apply out, having worked out that probability value, we apply out whatever threshold we decided on, typically 0.05, and use that to make a kind of a decision. Now, if we're using a 0.05 threshold, if our alternative hypothesis is just saying that our beta is not 0, that's what's known as a two-tailed hypothesis. So we're not particularly predicting that it will be bigger than 0 or smaller than 0, we're just saying it won't be 0, then that 0.05 probability gets split over the two tails of the distribution, because we're prepared to accept that the effect could be in either direction. But there's other scenarios where you might make a very specific prediction, and you're saying that there's a direction associated with it. So you're saying your beta is not only not going to be 0, it's going to be positive, for example. And in that scenario, you can put kind of all of your 0.05 probability in the upper tail, and that will give you a sort of a different threshold to apply to determine whether that result is significant, or that test statistic is significant or not. So that's your kind of standard process for calculating p. Now, what is a p-value? What does that p actually represent? Having got that probability, what does it mean? In order to explain this, we're going to think about a rather outlandish scenario where I'd like you to imagine that imagine a university that applies a very, very weird kind of system where all students rate all other students on various personality dimensions. So let's say every day you get a little notification from the university saying, can you please rate and one of your fellow students. So and you have to rate them along various dimensions, such as how funny they are, so a humour rating, how kind they are, how conscientious they are, so things like that. So you're just rating dimensions of their personality. And then at the end, there's a little tick box. Would you date this person? Because this is like a really weird university who likes to get involved in people's dating. So let's imagine that. Imagine you're at this university and like I say, every day you get to rate one of your fellow students along personality dimensions, and you also get to indicate whether you would date this person. Okay, now imagine two students. First student is called Alice. She is brilliant, very conscientious, works very, very hard, gets good grades, very studious. And because she's so conscientious, she diligently completes these ratings every day when she gets them, even though she kind of thinks, what's the point of this? But she diligently does the ratings. And I want you to imagine another student called Zach. And he's very, very nice guy, not so diligent though. He's like, he's in a band, he's a bit more laid back about his studies, but he really likes Alice because she's like so clever. He's just like, oh my God, she's so clever. I love her. But he's a bit shy. He's not quite sure whether, she would be interested in him because he's a bit low on his self-esteem, kind of think, well, I'm kind of really into my music, but I'm not so academic, and she's like brilliant, so maybe she wouldn't be interested in like a non-academic sort like me. But he thinks she's amazing. So, but he's not confident enough to ask her out for a date. So he like chats with her, says hi, whatever, but he gets a bit nervous. He can't actually bring himself to like ask her out. But he knows that there's all these ratings going on, all this rating going on. So he's like thinking, well, maybe she's rated me. It's possible. Anyway, one day he's in the library and, he's sitting doing some studying, getting a bit confused about, what the p-value represents. And, Alice is just over a few tables away, very diligently doing her statistics coursework. And he just kind of, you know, he's kind of got a bit bored of kind of looking forlornly at her from a distance. So he decides to like go and get a coffee or something. So he's just walking out of the library and he has to walk past her table. And as he walks past, he notices on her laptop, the app, the university's app is up, and he sees his photo. And she's about to rate him for humour. And he notices, just as he goes, because, you know, he doesn't want to like stand and stare at computers, that would be weird. So, but as he goes past, he just notices that she'd clicked on a 5 on this rating scale, so 5 out of 10 for humour. And, you know, then she submits it, moves on to the next rating, and he goes past because he's like, yeah, I don't want to hang around here. But he's got some useful information. That's his test statistic. His test statistic is he knows that Alice has given him a rating of 5 on humour, so 5 out of 10. In isolation, though, that test statistic is not particularly useful. You know, 5 out of 10. It's not. You know, it's not putting him in stand-up comic territory or anything, is it? So he needs some context for that. And the context is how Alice rates other people. And in particular, how Alice rates other people that she doesn't want to date. So what he does, he has a friend in computer science, and he gets the friend in computer science to like hack into the database, at which point, you know, this is starting to get quite unrealistic, but never mind, stick with me. And he finds all of Alice's ratings apart from his. Darn it, because his one hasn't been committed to the database yet. So he's got all her ratings. And what he discovers is that for the question, would you like to date these people? She's answered no to all of them. So he has a bunch of information about how Alice rates people on her module when she doesn't want to date them. That's the null hypothesis, is Alice does not want to date Zach. So he's suddenly got a load of information about how Alice rates people that she doesn't want to date. And in particular, if he looks at the humour ratings, he knows how Alice rates people that she doesn't want to date on humour. So this is like the distribution under the null, the distribution of humour ratings under the null. So he has this information, how she rates people that she doesn't, how she rates the humour of people that she doesn't want to date. And he's also got a test statistic. He knows that she rated him as a 5. So let's imagine one scenario where this is the distribution of Alice's ratings of people's kind of funniness when she doesn't want to date them. So this is her distribution of humour ratings under the null. Now in this scenario, you can see that on average, her rating's around 6. So when she doesn't want to date people, on average, she'll give a rating of about 6 for humour. So kind of, you know, sort of midway along the scale. If we look at high ratings, say a rating of like, you know, 8, it's very rare that she gives a rating above 8 when she doesn't want to date someone. And it's very rare because she's a nice person. She doesn't really rate people's humour very often below about a 4 either, because, you know, she's too nice to give people 0s and 1s. Now Zach knows he got a rating of 5. So what this information tells him is the probability that she would give a rating of 5 or more if she didn't want to date someone. And that probability is the area under this curve. And what you can see is it's a big area, right? So she quite often gives a rating of 5 to people that she doesn't want to date. Remember, Zach's test statistic is 5. That's the rating he knows that she gave him. So should he accept the null in this situation? Well, he knows that when she doesn't want to date people, she quite often gives a rating of 5 or more. So it's quite likely, given he's got a rating of 5, you know, that's consistent with the null hypothesis. It's consistent with her not wanting to date him because she quite often gives people a 5 or more if she doesn't want to date them. So really, this provides a context for his test statistic. Now let's imagine a different scenario. So let's imagine her ratings look like this. So in this scenario, Alice hardly ever gives a rating more than 6 when she doesn't want to date someone. Basically never does it. So how does Zach's rating of 5 shape up if this were her distribution of humour ratings? Well, in this scenario, it's looking a bit better for Zach, to be honest, because she very, very rarely gives a rating of 5 or more when she doesn't want to date someone. So his rating of 5 is fairly inconsistent with how she rates people that she doesn't want to date. It's very, very uncommon that she gives ratings as high as 5 to people that she doesn't want to date. So this would kind of give him some hope, I guess, that maybe the null is not true. Maybe he can reject the null and instead assume that she might want to date him, because his rating is quite high for someone that she doesn't want to date. So maybe she does want to date him. So what is the p-value? Well, it's very, as I said, it's very misunderstood. So it's the probability of getting a test statistic at least as big as the one that we have observed, given that the null hypothesis is true. And we can look at some things it's not as well. I'm going to enlist my friend, Professor Hippo, again here. And imagine some, scenarios. How are you, Professor Hippo?
Yeah, not too bad, not too bad.
What have you been up to?
I've been doing a little bit of anger management.
Ah, that's good. So we're going to do a little scenario where I'm going to give you some definitions of a p-value and see what you make of them.
Okay.
But I don't want you to hit me this time. That kind of hurt last time.
No, you're all good. I've been doing meditation and everything. I'm good. I'm calm. Super calm. I'm so calm.
Nice. Okay. So the p-value is the probability of a chance result. I thought you said you were calm.
Yeah, that threw me over the edge. Sorry.
Okay, the p-value is the probability that the null hypothesis is true. Seriously? The p-value is the probability that the alternative hypothesis is true. So it's not any of them then?
No. It's the probability of getting a test statistic at least as big as the one we have, given the null hypothesis is true. Don't forget it.
Oh, thanks for that, Professor Hippo. So bear in mind, p-value, it's not the probability of a chance result. It's not the probability that the null is true. It's not the probability that the alternative hypothesis is true. Now, some constructs related to the p-value. First is a type 1 error. This is the probability of rejecting the null when it is in fact true. So this is kind of like believing in effects that don't exist. And, it's not good. It's not good to believe in things that don't exist. Well, I mean, there are some unicorns. It's probably okay to believe in them. But generally, try not to believe in things that are not true. Well, unless it makes you happy, then it's kind of fine, isn't it? I mean, what am I getting on about? So this is a bit like Zach believing Alice wants to date him when in fact she doesn't, which is awkward. Type 1 errors. Awkward. Type 2 errors. This is accepting the null hypothesis when in fact it's false. So this is not believing in effects that do exist. So this is a bit like Zach believing Alice doesn't want to date him when in fact she does. Sad story. So type 2 errors, sad story. Type 1 errors, awkward. And statistical power, it's the probability of a test avoiding a type 2 error. So in other words, it's the probability that a test detects an effect that is in fact true. Or another way of putting it, the probability of rejecting the null when the alternative is in fact true. Okay, let's move on to an example that we're going to use throughout the rest of the lecture. So this is an example based on teddy bear therapy. And to illustrate this, this is my eldest son helping me out here. Well, the photos are a couple of years old. So he's my eldest son. He's my wife's eldest son as well. And frankly, she had a much bigger contribution to his production than I did. So imagine a scenario where we were going to look at teddy bear therapy. So whether hugging a teddy bear could improve your self-esteem. Now we need some kind of control group for this. And the control group we might choose is hugging, something else, like a statistics textbook, for example. Now, like his father, my son here does appear to be happier when cradling a statistics textbook than when cradling a teddy bear. I mean, hopefully there's enough time for environmental influences to drum that out of him. But he's getting on the statistical ladder early. Good work, or bad work, depending on how you look at it. So we've got two conditions, a group of people who have teddy bear therapy, a group of people in some kind of textbook hugging control group. I'm not sure you'd get that past ethics, actually, giving people one of my books to read as a control. But anyway, we're going to use this example to illustrate some of the problems with null hypothesis significance testing. So the first problem is that hypothesis testing doesn't tell us anything about the importance of the effect, despite the fact you use the word significant, because the p-value depends upon the sample size. Now, we're going to illustrate this with, imagine this teddy bear study was done 3 different times. So you can end up with scenarios. Here's the first study. So in the estimate column, we've got a -5. That's the difference in the mean self-esteem between the 2 conditions. So that's our effect. So having a teddy bear to cuddle, well, actually, it depends which way around you do it. I'll phrase it the other way around because it's easier to think about. Having a book to cuddle rather than a teddy bear reduces self-esteem by 5. And if you're looking at the P for that is 0 to a few decimal places. So basically, very, very significant effect. In study 2, we have exactly the same effect. So self-esteem changes by 5 on our self-esteem scale, but now the p-value is not significant. It's only it's above the threshold of 0.05, so we conclude it's a non-significant result. So here we've got 2 different studies that have the same effect size, the value of the parameter is identical, but we get different p-values. That's weird. Let's have a look at this other study. We've got study 3, we have a 0 effect roughly. So the size of the parameter is 0.052, so it's basically 0. There's basically no difference in self-esteem between the book condition and the teddy bear condition. But if we look at the p-value, it's 0.046. It's below our 0.05 threshold. It is significant. So that's weird. We've got basically no difference between the groups, but that's coming out as significant. So why is that? The reason is to do with sample sizes. So study 1 had 200 participants. Study 2 had only 20. So the reason those studies have the same effects but different p's is because they're based on different sample sizes. So what that means is, or what that illustrates, is that the p-value has a relationship to sample size. So in big samples, p-values can be small even when the effect is kind of trivial. And in small samples, big effects can be non-significant. Now, if you take this to its kind of logical extreme, in study 3, how did we manage to basically have an effect of 0 that was significant? It's because our sample size was massive. The sample size in this study is 200,000. So the P comes out as significant. It has so much power to detect even a trivial effect. The moral of this story is, whenever you look at a p-value, you should always interpret it within the context of the sample size. If the sample size is huge, then a p-value can be significant even when the effect is trivially small. Another problem with null hypothesis significance testing is it provides little evidence about the null or alternative hypothesis. Now, firstly, it assumes that the null is true, because remember, we're calculating a p-value under the assumption that the null is true. So we're using the distribution of the test statistic when the null is true to calculate p. So we're assuming the null is true to get p. If we get a p-value greater than our threshold, so say greater than 0.05, all this means is that the effect was not big enough to be found given our sample size. It does not mean that the effect is 0. It does not mean that the null is true. And if we get a p less than 0.05 or less than whatever threshold we've set, it just means that the observed test statistic is unlikely given that the null is true. But that doesn't mean that the alternative hypothesis is true. So going back to our example of Alice and Zach wanting to know whether Alice was likely to want to date him, his humour rating of 5, he could take that, he could know that that was an unlikely rating if she didn't want to date him, but that doesn't mean she actually wants to date him. So, there's a kind of a leap of faith there that you're making. It's also based on a kind of flawed logic. So to explain the logical flaw, we'll have a bit of Iron Maiden. The kind of logic of the null hypothesis, or of significance testing, goes something like this. If the null hypothesis is true, then it is highly unlikely to get the test statistic that I have observed. I have observed this test statistic, it has occurred, therefore the null hypothesis is highly unlikely. That's the kind of logic that it relies on. Now this seems kind of at face value to be okay. I'm going to switch some of the words and show how it's not actually very logical. So I'm going to replace the phrase null hypothesis with the phrase person plays guitar, and I'm going to replace the phrase test statistic with plays in the heavy metal band Iron Maiden. So rephrasing null hypothesis significance testing is a bit like saying if this person plays guitar is true, then it is highly unlikely that he or she plays in Iron Maiden. Now, in fact, this is a completely, true statement. There's about 50 million people on the planet that play guitar. Not counting the bass guitar, because that's not a proper guitar. It's about 50 million people play guitar, and only 3 of them play guitar in Iron Maiden. So out of the 50 million people that play guitar, it is very unlikely that the one you happen to have picked plays guitar in Iron Maiden. So that's true. So the next thing, this person plays in Iron Maiden. So we happen to have observed someone, and the person we've observed happens to be one of the guitarists in Iron Maiden. Therefore, person plays guitar is highly unlikely. Well, is this true? Actually, it's not true, because there are 6 members of Iron Maiden, 3 of them play a proper guitar, so 50% of them play guitar. So if the person plays in Iron Maiden, then actually it's pretty likely that they play a guitar, or because half of them do. So hopefully you can see that the kind of the logical statements do not necessarily follow. By replacing null hypothesis with person plays guitar and test statistic with plays in Iron Maiden, you can see that if you follow the statements through, you can get to a nonsensical result. So it's not actually a logically coherent process. So it tells us nothing about the importance of the effect, because P depends on sample size. It provides little evidence about the null or alternative hypothesis. I'm really selling it to you here. The other thing is it encourages all or nothing thinking. So what do I mean by this? Well, one of my hobbies when I'm not lecturing statistics is to set up webcams in the offices of my colleagues around the psychology department. And I record hours and hours and hours of footage. And then I kind of work through it and look at what they get up to in their offices. And in particular, I'm interested in when they're analysing data. So I hone in on that moment when they've fitted their model and all the results come up on their screen, and they're kind of scanning their results and seeing kind of what happens. And I've got a little montage here of some of those recordings for when members of faculty have fitted their model, and the key effect they were interested in has yielded a p-value that's greater than 0.05 or greater than the threshold they were using. So they've scanned through and seen that their effect was non-significant. This is what happens. Now, feel free to work out which animal was which member of faculty. I can possibly comment. Basically, everyone's really distressed. They've spent all this time doing this research, and then their p-value is not significant, and they all start screaming and making horrific noises. Here's a clip of someone that I found where when they fitted their model and scanned through their results, they found a significance value, a p-value less than 0.05, which was their threshold. So they found a significant result. They are happy with what's happened. So a big problem is that focusing on p-values tends to encourage all or nothing thinking. Either the effect is significant, yay, or it's non-significant, sad face. And it's like there's kind of nothing in between. And of course, unfortunately, it's much easier to publish significant results in journals. So there's a whole incentive structure set up in science whereby you are reinforced for significant results and kind of penalized for non-significant results, when actually non-significant results, can be interesting, or there's a wider context around the significance value. So going back to our teddy bear therapy example, where we had a group of people cuddling teddy bears and a group of people cuddling statistics textbooks, and we measured their self-esteem. So we did that study. Imagine 9 other research groups around the world did basically the same study. And these are the results of those 9 studies and our original study. So what we've got here along the x-axis is the difference between the group means. And for each study, there's a dot representing the difference between the group means for that particular study. And each dot has a 95% confidence interval around it, representing the confidence interval for that difference. Now, notice there's a vertical dashed line, and that's at 0. So that's representing the null. So that's representing the fact that there's no effect of teddy therapy. There's no difference between the means in the teddy therapy group and the book group. Anything below that line, that's saying that self-esteem was higher in the book condition than in the teddy condition. So in other words, cuddling a book was more effective than cuddling a teddy. And anything on the right hand side is the effect that we were expecting, that cuddling a teddy yields higher self-esteem scores than cuddling a book. Now let's have a look at the p-values for each study. So each study has a p-value for this difference, p-value for this effect. So we can see in there, some of them are, and let's say we're using a threshold of 0.05. Some of them are significant. First study is significant, second one's not, third one's not, and so on and so forth. Just take a moment to think about whether you believe teddy therapy has an effect based on what's in front of you. Now, what you might have concluded is that teddy therapy probably doesn't have an effect. The results here seem quite inconsistent. So the first study 10 is significant, study 7 is significant, study 6 is significant, and study 4 is significant. So 4 of the 10 studies get a significant effect. The other 6 do not. So you might think, well, it probably doesn't work. 6 out of 10 studies show a non-significant effect. However, by focusing in on the p-value, you're ignoring a lot of the consistency in the data. So, for example, all of the dots, all of the point estimates in every study all fall to the right-hand side of 0. So they all show, or every study shows, an effect where self-esteem is higher in the teddy condition than the book condition. So there is actually a lot of consistency. And all the effects are within a fairly narrow threshold. So the effects are all between a difference of about 1 in the means and a difference of about 4 between the means. So there's actually a lot of consistency here, but by focusing in on the p-values, our attention is drawn towards differences. So we're sort of saying, well, 4 studies say it works and 6 studies say it doesn't, so it probably doesn't work. But if you look at the actual estimates, the actual parameters themselves, you're seeing a lot of consistency in what those studies are showing. So it tells us nothing about the importance because p depends on sample size. It provides little evidence about the null hypothesis, encourages all or nothing thinking. And the other thing is it's based on long run probabilities. So its job is to control error rate in the long term. So p is the frequency of the observed test statistic relative to all test statistics from an infinite number of identical experiments with exactly the same a priori sample size. So its telling us a long run probability. It's saying that in the long run, if we interpret significant results as significant, in the long run, we will only be wrong 5% of the time. The p-value is not a probability attached to our particular study. It's a kind of an error rate attached to all the studies we might conceivably do. So it's a bit like, so, you know, if you're going to have a long academic career doing lots and lots of research, and what you really care about is controlling the type 1 error rate over the course of your career, that's what the p-value will do. That's kind of its job. But if you're interested in, is there a significant effect in this particular study that I have done, it doesn't tell you that. The type 1 error rate in a given study is either 0 or 1. You've either made a type 1 error or you haven't, but you don't know which it is. But what you do know is in the long term, over lots and lots and lots of studies, you will only make a type 1 error, say 5% of the time, if you use a 0.05 threshold. So you've got to be clear about what the p-value does. It provides long-term error control. It doesn't give you a probability for your particular study. So rather than obsessing over p-values, you can also interpret the effects themselves, and this provides a useful context. And there's a few ways you can do this. We talked in previous lectures about raw effect sizes, so actually interpreting the betas, the B's. I'm a big fan of this. You'll also see people using standardized effect sizes. So these are effect sizes that are expressed in standard deviation units or some other kind of standardized unit. So a few common ones are Cohen's D, Pearson's correlation, and we came across the standardized B in a previous lecture. So that's like the model parameter, but expressed in standard deviation units. So to give you an example of Cohen's D, because we haven't talked about that one yet, all you would do here is take the difference between the two means. That's what this the top equation is kind of saying. So you take the difference between the two means and you divide it by some kind of estimate of the standard deviation. So the top half of this bit here, that is just the raw effect size. It's the raw difference between means, and you standardize it by dividing by some estimate of the standard deviation of scores. And there's a few ways you can do that. It's quite common in clinical studies to just use the control group standard deviation, because that would be that would be a sort of a good, I guess, baseline of variability in scores. But you also sometimes see the pooled standard deviation. This is basically like a weighted average of the standard deviation across the two groups that you're comparing. So let's have a look at how effect sizes can contextualize a p-value. So going back to our 3 teddy bear therapy studies, if you remember the first 2, they had the same parameter, so the same difference between means. So in both studies it was 5, but in one study the p-value was basically 0, and in the other study it was 0.1. So if you look at the p-values in these 2 studies, you would conclude the opposite things. In one study, teddy therapy appears to have a significant effect, and in the other study it doesn't. If we focus on the parameter itself, or the raw effect, then we would reach the same conclusion from these 2 studies. So the effect on self-esteem of teddy therapy relative to a book is a change of 5 on the self-esteem scale. So by focusing on the effect size, we contextualize the p-value. So we're drawn away from this kind of all or nothing thinking. When the effect is the same, the effect is the same in the 2 studies. Similarly, if we look at that study where we had a 0 effect, so basically the difference between means was 0, but the p-value was significant, well, we can get very excited about our significant p-value, but when we look at the effect size, the raw difference between means, and we see that it's 0, that contextualizes the p-value for us. So we know, okay, this is significant, but actually the effect is trivial, so let's not get too excited about our p. So effect size is a really useful way to contextualize a p-value. Going back to an example that we used in previous lectures, so this was some research done on whether playing hard to get predicted romantic interest in someone. And this is a slide from a previous lecture, and it's just really to highlight the fact that we have looked at raw effect sizes before in previous lectures, so they are a familiar thing. There's nothing new here. So we saw, for example, we got a parameter estimate here of 0.294. That's a raw effect size, which told us that as the perception that the other person was hard to get increased by 1 on a scale that was 1 to 5, it was associated with 0.294 more expressions of interest. And if you remember from previous lectures, we talked about that being a very small effect, because you'd actually need perceptions of playing hard to get to increase by 3.4 on a 5-point scale to even get 1 additional expression of interest. So raw effect sizes are familiar. Now, what happens if we go back to this diagram, so where we looked at our 10 studies of teddy bear therapy, and we looked at the p-values, and we concluded there's inconsistency in the results. 6 studies say there's a non-significant effect, 4 studies say that there's a significant effect. And I said this kind of focuses your attention on inconsistency. What happens if we look at the effect size? So I've got the effect sizes here expressed as Cohen's d. So this is the difference between means expressed in terms of standard deviations. So for example, in study 10, the difference between means was 0.7 of a standard deviation. The main thing to focus on here is how, again, effect sizes help us to focus on consistency in this case. So all of the effect sizes, all of Cohen's D's are positive values. So they all show that teddy bear therapy yielded higher self-esteem scores than the book therapy group, or the book control. So there's consistency. All the studies, D is positive. And also, if we look at the magnitude of D, it's also fairly consistent. Most of the Cohen's D's fall between, 0.45 and kind of 0.7. So there's actually a reasonably narrow range of effect sizes here, reasonably narrow. But again, we can see consistency here. So the effect sizes become a useful contextual factor here. So although we've got inconsistency in the p-values, the effect sizes are showing us that the studies are actually showing quite similar things. And bearing in mind the p-values in the different studies will have been affected by sample size and things like that. So just to summarize, model parameters typically, so the B's, typically represent hypotheses, and we can test whether those parameters are different from 0 as a way of testing the hypothesis, testing whether the effect is different from 0. And we do this by computing a p-value. And a p-value is the probability of observing a test statistic at least as large as the one we have, given that the null hypothesis is true. And this process is somewhat problematic. So in a way, it addresses the wrong question, because I think most people probably actually want to know, the probability of the effect being real in their particular sample. That's not what the P tells you. P's are dependent on sample size, and they do encourage all or nothing thinking. So although it's fine to use p-values and they can be useful, they should always be interpreted in the context of the sample size and in the context of the effects, the raw effect size or a standardized effect size. Okay, that's it. Thank you very much.